Good morning. Today we will present our project on floating point adder hardware, focusing on the IEEE 754 single precision format and the hardware data pad used to perform floating point addition. In floating point computation, the IEEE 754 2008 single precision format defines how numbers are represented in 32 bits. It consists of 3 parts. 1 bit for the sign, 8 bits for the exponent with a bias of 127, and 23 bits for the fraction or mantissa. The value represented follows the formula minus 1 to the power of s times 1 times f times 2 to the power of e minus 127. For example, the number 1.0 has a sign of 0, exponent 127, and a fraction of all zeros. Adding floating point numbers is more complex compared to integers because the binary points of the number may not be aligned. Therefore, a floating point adder requires multiple states to correctly align, add, normalize, and round the values. These states work together as a complete hardware data pad. The key states of floating point adder are swap and complement. We first check which operand has the larger exponent and ensure it becomes the primary input. If the signs differ, this state also prepares for subtractions. Exponent difference. We compute the difference between exponents to know how much to shift the smaller mantissa. Mantissa alignment shifter. The smaller number is shifted to the right by the exponent difference, and bits shifted out contribute to the sticky bit for rounding. Mantissa adder or subtraction. The aligned mantissas are then added or subtracted depending on the sign bits. Normalization. After addition, the result may not be normalized. We use a leading zero counter to determine how many positions to shift left. Rounding. The result is rounded according to round to nearest times to even. Finally, we assemble the sign, exponent, and mantissa back into the standard 32-bit IEEE format. Datapad diagram. This is the full datapad that combines all the stages. It shows how the number flows through comparison, shifting, addition, normalization, and rounding before being packed into the final floating point representation. Next, we describe each module more clearly. Exponent, comparator, and subtractor. This block compares the exponent of A and B and computes their difference. This determines the amount of right shifting. Swap and complement marks. If exponent B is larger, the system swaps the operand to maintain consistency. If subtraction is required, signs are complemented. Mantissa alignment shifter. A barrel shifter shifts the smaller mantissa right by the exponent difference. Shifted bits contribute to the sticky bit. Mantissa adder or subtraction. A 24-bit adder performs addition or subtraction based on operand signs. Normalization shifter. After addition, the result may need left or right shifting. A leading zero counter detects how many left shifts are needed. Rounding unit. The RNE round to nearest even rounding rule is applied. If rounding overflows, we know normalization may occur again. The control unit determines when to swap operands, when to complement signs, and whether to add or subtract. The truth table outlines the behavior for all combination of signs bit. The logic allows the secret to handle A plus B, A minus B, minus A plus B, and minus A minus B correctly. Here we show the logic diagram. Swap integration uses sign A and not sign B. Complement is sign A XOR sign B. Add or sub is also determined by sign A XOR sign B. This simple gets result in correct behavior for different sign in input combination. Rounding hardware. In round to nearest ties to even, the decision depends on 3 bits: the guard bit, the round bit, and the sticky bit. The sticky bit is the OR of all bits shifted out during alignment. Based on the combination of these bits, the rounding unit The Unite decided whether to increment the mantissa. Let's walk through an example. 10.75 in binary is 1010.11, which normalized to 1.01011 times 2 to the power of 3. 0.125 in binary is 0.001, which normalized to 1.0 times 2 to the power of minus 3. Their exponents are 130 and 124 respectively. So the exponent difference is 6, meaning the mantissa of 0.125 is shifted right by 6 positions before addition. After alignment and addition, the number is normalized and rounded. The final result matches the expected value of 10.875, showing that the FP adder functions correctly. We use ChatGPT to understand the floating point adder data pack by asking for step-by-step explanation. AI clarifies concepts such as the sticky bit and normalization. It helps create clear module descriptions and guided us through the design process. AI also helps us construct truth tables and verify our reasoning by giving scenarios such as A plus B or A minus B. With different sign combinations, we validate the correctness of swap, complement, and add or sub signals. We also use AI to generate this presentation outline. We ask for slide structures and explanation for each component, which help us organize our content clearly and visually. Thank you for listening.